Thank you very much for the invitation. I will talk about diagrams in quantum field theory, what you can do. I will start from the basic, brief recall of what we know, Feynman diagrams, and then I will move to more general diagrams that might be familiar to some of you or not, like those that are used for in correlation functions, for example, Keldysh, Schwinger, or the Cutkosky-Veltman identities. And then we will fly away to explore new frontiers, new possibilities, new diagrams. And then we will see what we can do with that. So quantum field theory is, to a large extent, at least perturbative quantum field theory expressed by means of Feynman diagrams. Let's say in general diagrams. And I will start by comparing known type of diagrams, Feynman, diagrams that I will call Cutkosky-Veltman diagrams and Keldysh diagrams, and then I will introduce diagrams of new types. Because using this tool, we will be able to define new types of particles, which I will call purely virtual particles, and new types of theories. And this opens the way to do something new, including a proposal for the quantization of gravity within quantum field theory. I also will talk about how the diagrammatics works, how you can formulate quantum field theory in a finite interval of time and on a compact space manifold, because normally what we do is S-matrix amplitudes for scattering processes that are tested at CERN, and so they are supposed to occur between -infinity in time and +infinity in time. Well, you need to go beyond that to appreciate many otherwise hidden properties. And then I will discuss dress propagators when you resum the geometric series of the self-energies, what happens when you are on a space on a finite interval of time or a finite space manifold. And then I will discuss predictions that you have from these ideas in phenomenology and finally in cosmology, with a very sharp prediction for the tensor to scalar ratio R, which is a quantity that is being measured today, and probably in some 10 years or 15 years we will know the value of this quantity. So let's start from a Lagrangian. I will prefer the Lagrangian approach. We will see that for these new types of particles, the Hamiltonian approach is problematic, but the Lagrangian approach is clear, and we separate it as usual in a free part and an interaction part. The free part provides the propagators by means of the usual Feynman prescription, which means time ordering, and then the interaction part provides the vertices. Then we build diagrams, and these diagrams have what meaning? They are in-out correlation functions, so-called, and they allow us to build the S-matrix amplitudes. But there are other types of diagrams that you can consider. Some of you might have heard of them, some others might not, because they are not very common. For example, one might be interested in correlation functions, which are Keldysh-Schwinger approach, Keldysh diagrams, I will call them. Or you might be interested simply in cross-sections rather than amplitudes, diagrams to study the optical theorem, unitarity, and these are, I will call Cutkosky-Veltman diagrams. Or you might want to use prescriptions of a different types instead of the Feynman I epsilon. I will not do that. Just use the Feynman I epsilon and then define in some way new prescriptions by means of diagrams built with that, however. So let me tell you about what we all know: basic ingredients, propagators. This is the Feynman propagator, and vertices, for example, a cubic vertex, like here. And then with these things you build diagrams. Okay. What can you do away from this? You can, for example, use new ingredients and new rules. Take propagators and vertices and add conjugate propagators and conjugate vertices. And then you add new types of propagators in between, which we will call Keldysh, Cutkosky-Veltman, Weidman propagators. Just take the average of a product of two fields. Instead of a time-ordered product of two fields, just the product. Operator, field, field operator, x, y. In momentum space, this is it. Its own shell. And it amounts to integrating on the phase space. So if you build the diagrams that I tell you about now, you build the Cutkosky-Veltman or Keldysh diagrams. Basically, they are divided in two parts by a vertical bar, which we will call a cut. And then there is a shadowed side where you have the conjugate propagators. If a line is entirely there, it's a conjugate propagator. If a vertex is there, it's a conjugate vertex. And here you have anti-time ordering. Then you have a left side where you have vertices and propagators. And then you have legs that cross the cut and connect two different sides. Those are cut propagators. So this is a definition, a well-defined formulation of new types of diagrams. Basically, when you have two field insertions that happen to occur to the right, you have anti-time ordering. If you have two field insertions to the left, it's the usual time ordering. But if you have one field insertion to the right and one to the left, then with the Wick's theorem, you use this propagator. And you draw all the diagrams that you can draw. And actually, the diagrams I'm talking about, which I name after Cutkosky-Veltman or Keldysh, are sums of diagrams like these. Let's see what we can do with those. You can study the so-called in-correlation functions or the time evolution of averages, more or less what you would do in quantum mechanics, rather than what you normally do in quantum field theory, or what you do in primordial cosmology. Those are in-correlation functions and not the spectra, and not in-out. Or the square moduli, the cross-sections, the optical theorem, unitarity. For example, if you want to express this identity diagrammatically, S dagger S equal 1, you see S dagger S is a product of two things, and so you have diagrams made of two parts. One is conjugate and the other one is not conjugate. And a certain sum of those diagrams with the shadowed part that can shadow the entire diagram. So this is like saying you have a diagram. So this is like, the first one is like saying that you have the entire diagram to the left of the vertical bar, or the entire diagram to the right of the vertical bar here, or you have the vertical bar in the middle. Then you apply the rules and you sum all those things and you find 0, which is a way to phrase a certain contribution of the identity S dagger S equal 1. Or in the triangle you can make the sum of similar contributions where I mark the shadowed vertices by means of a big dot. And so here the cut would be here, for example. The shadowed region is this one, here the shadowed region is that one, so on and so forth. And again the sum vanishes, and this is something that translates S dagger S into diagrams. If your theory is unitary, the sum should vanish. If your theory is not unitary, the sum does not vanish. In the Keldysh case, you can sum these contributions, these diagrams, because you want, for example, to build new propagate different green functions like the retarded potentials. If you want to build the retarded potentials, you can make the sum of Feynman plus the on-shell part, which I call Weidman or cut propagator, that is necessary. So you have, if you're familiar with Keldysh diagrams, you have to double the number of fields in order to put these things together and build new diagrams. So this is just to remind you that it's not uncommon to go beyond Feynman and study different things. What are we doing when we do this? Well, certainly we are not changing the theory. The theory is always the same. We are just changing the viewpoint of the theory. We are changing the quantities we are interested in. Instead of in-out correlation functions or scattering processes, we are studying, for example, averages of composite fields or square moduli, but the theory is always the same. Okay, you cannot change the theory just by juggling on its ingredients. So for the moment, we will just continue this exercise of building new things, and let's try and see what we can obtain if we just consider the most general possible ways of building diagrams. So I will describe the contents of this recent paper. So let me first give you the ingredients. The ingredients are, again, vertices and propagators, as in Feynman. But you forget completely about the conjugate propagators and the conjugate vertices. And then you add the cut propagators. With one difference with respect to before, now you consider arbitrarily many cuts or vertical bars. And so you build diagrams like these. You have an arbitrary number of vertical bars, 1, 2, 3, 0. And then you distribute all the vertices you need to consider to the order you are computing. In between, you have many strips. And then you can connect the vertices in all the possible ways. And when a leg is entirely in one strip, it's Feynman. When a leg is, so this, when a leg crosses one or more cuts at the same time, could be more, could be a vertex from here to here, for example, then it is a cut propagator. This is something you can do. So what is it? What is it like? So remember that previously we had diagrams divided in two parts, where you have S, dagger S. Here you have anti-time ordering. In this part you have time ordering. And what is this? The thing that connects the two is just the product. You see, this is the product of two matrices, S, dagger, S. It's just a product, not a time ordered product. That's why you do not have time ordering, but you have the Whiteman propagator. So here we have infinitely many cuts, or an arbitrary number of cuts, which means that we are multiplying S. S times S times S. So basically, instead of studying the usual S matrix, we are studying a function of the usual S matrix by summing powers of the usual S matrix. That's just what we are doing. We are not studying S dagger or S dagger S, but just S times S times S times S. Let's see where we can go. So what are these diagrams good for? So we want to use these diagrams to change the S matrix, basically. You start from the original S matrix, and then I tell you, no, the right S matrix is a certain function of the usual S matrix. And what would we like to achieve by this? Solve some problems. Otherwise, this is just an exercise. For example, some long-standing problems that happen when you, for example, have some ghosts in your theory. Then you have a sick S matrix. The initial S matrix might not be good, but the final one that you build this way might be good. So this is the idea. So we replace the S matrix of a theory that has some problem, or even a theory that has no problem, with another S matrix. So the starting S matrix is the one built with the usual Feynman diagrams, and then we will replace it by means of a new S matrix, which actually, this is important to keep in mind for the rest, although I do not explain now. It's a projection. What the true S matrix, the physical one, will be is a projection of this function. But for the moment, it's just a function of the S matrix. So it's a function of the old diagrams, or a new S matrix built with the new diagrams, which is the same thing. Okay, so every strip is a normal Feynman diagram. This one, for example. In between the strip, you have those cut propagators, which is like multiplying matrices. So basically, you have, in this case, a contribution to the product S times S times S times S. And then you build a series, and you can ask, okay, but you have to sum many diagrams to replace one diagram. Precisely as in Keldysh, for example, you sum two propagators to build the retarded potentials. the Feynman propagator and the cut propagator. You sum them, you build the Feynman. With the right coefficient, you build the retarded potentials. And so who gives you the coefficients of the sum? Well, this is a requirement. We want to make sense of a sick theory. So let's see what we can do, because there is only one answer to achieve that goal. So let's describe the problem. So normally, if everything goes well in your theory is unitary. S dagger S is equal to 1. You can phrase it in many different ways. This is the usual decomposition. You take out the identity because it's trivial, and you separate the rest IT. I will write the rest as V, because I don't want many I's around. So normally this S dagger S equals 1 is written that way. You can call that the optical theorem. I will write it in another way, by means of the matrix V. So if everything goes well, this is what you have, unitarity. But suppose that you have some problem in your theory, like ghosts. And then you try and quantize them. Ghosts are what? They are fields with a negative sign, the wrong sign, in front of their kinetic terms. So we said you start from a Lagrangian, quadratic part, vertices, quadratic part with the wrong sign. That's what I call a ghost. And that minus sign reflects into this identity, because you will not have this identity or this identity. You will have some minus signs around, very annoying, very unphysical, and you would like to get rid of them. So instead of having 1 in between this product, you see this product is an identically negative definite matrix, minus T dagger T. This won't be identically negative definite, because you will have some C which, once diagonalized, will contain and normalized minus 1s as well as plus 1s. There can be some zeros, forget about those, because they could be auxiliary fields. We integrate them out. The crucial thing is that if you start from a theory that has fields with kinetic terms multiplied by the wrong sign, that wrong sign reflects into this identity, and then you call them ghosts, because that means that you do not have unitarity. It's like saying you have minus 1 particles. Physically, it's like saying you will find a cross-section that is negative, a probability that is negative. You can rephrase this thing many ways, different ways, but you will never get rid of the problem. You can use negative norms. You can have unbounded Hamiltonians instead of this. A Hamiltonian that is unbounded from below already at the 3 level. Let me focus on this, and we'll tell you in this formalism how you get rid of these minus signs, and then you can switch to the formalism you prefer. So if a theory has this, it is an unphysical theory, a theory that has ghosts. Although there are some people around who believe in ghosts. I think that Hawking also wrote a paper entitled Living with Ghosts. Maybe it's my prejudice, but for me these theories have to be discarded. Or not. Or yes, actually. These theories have to be discarded, but nevertheless we can use them to get to the right theory, and we will have to change the theory. So imagine like a rocket. You want to launch something orbiting around the Earth. Well, you have a rocket that's made of several parts, and several parts have to be detached along the way, and only the tip will arrive. So let's play in an exercise with matrices. We want to get rid of the bad part. And let's say you have this identity. So to the left, this would be minus V dagger CV, and I write C as the sum of A and B. And what are A and B? This is just an exercise with matrices. So I want to show you now a very general property that you can test yourself. A and B are anything you want, Hermitian matrices. But in our example, B will be the bad part with the minus signs. A will be the good part with only plus signs in the diagonal. So in B, there will be plus ones and minus ones. In A, only plus, and C is the sum. So A is the good, B is the bad, and C is the ugly. We want to get to a new V, or new S matrix, which I call reduced V, so as to get rid of the bad part. And what do? Well, you start taking this one, you move it to the left, and you try to redefine V in order to distribute it between the two, and see if this goes somewhere. Well, it does. And you can do it to all orders. Now I can show you the general solution, which is implicit. We will not need to use it, because I will skip the details. But basically, you have a certain formula for the new V, and so the new S matrix, which satisfies the clean identity, the one you would like, or something forward, towards the one you would like, which is a sum, you see, of many, many terms, like before, many, many diagrams, V times V times V times V. So these are diagrams built with many cuts and many, like the ones I described previously. And the formula contains V itself, so this, contains the bad matrix, B, contains the good matrix, and also it contains an arbitrary anti-Hermitian matrix, because there is an ambiguity in the solution. I don't tell you what it is useful for, but the good solution is determined by choosing omega appropriately, because otherwise, if you build the new diagrams like that, you will not have many, many properties that you are normally accustomed to, like the fact that you have generating functionals usually for connected diagrams, for one particle irreducible diagrams. Unless you choose omega in a certain way, you will not have those. But there is a solution. So there, in the end, there will be a unique solution. Yes?
Is it sort of BRC formulation level PS matrix, or you just defining some sort of way with your...
Let me go to I will explain some. The answer is no, but yes. But no. But you're right in trying to find a connection there. It's something similar without a symmetry, because that's precisely what I wanted to do here. Something similar to that, but without a symmetry, protecting me and leading me to that. Okay.
Are you trying to basically find a new Lagrangian for the theory?
The Lagrangian will be the same, but as you have pointed out right now, you should not look at the starting Lagrangian as the final Lagrangian or the one of your theory, because that would be sort of a gauge-fixed Lagrangian. It contains something redundant. But there is no other way than starting from that, as in the rocket metaphor, because otherwise you would have to use non-local things and many more complicated things.
But do you still retain the notion that the S matrix is a solution to a time evolution equation?
No.
You don't retain that?
No. We'll comment on that at the end. It's a solution of something, who knows what. So, okay, I've done this exercise, I've cleaned the identity, and then one can object. Other objections are very natural. For example, your main objection is you are still in the same theory. You have been juggling with the same ingredients. You have built new things, new V's, new S matrices. The theory was not unitary before. The theory is not unitary now, because the theory is still the same. You might change the reference frame. You view the same theory under a different viewpoint. That does not mean you have solved the problem. And this is correct. But why is it correct first? Because now I have removed the bad part, yes, but I still have these zeros. And this is not good for unitarity. It means that if you have something outside, in and out state, it can disappear into zero. This is not unitarity. You have to remove that thing. because the good thing is that now when you have changed the viewpoint like this, and you watch your theory from that viewpoint, you say, aha, I can make a projection now. Which means that if I remove all the in and out states that correspond to these intermediate states from in and out, they will not reappear inside, and in a subspace, the projected subspace, I will have a new theory this way. So this is the point, the crucial point, where I switch from the old theory to a new theory by guillotining, using a guillotine, or slashing out all the bad things. So we can make a projection by dropping all the states that are responsible for the zeros in the diagonal block. And then if you eliminate from in and out with the new diagrammatic rules that I've told you, they are not resuscitated inside. Okay, so you have this, this was the starting identity with the bad part, B. And C is a diagonal with many plus ones, but also minus ones, forget about the zeros. A, you can view now this A as a projector onto the physical subspace, and the new physical amplitude will not just be the one I told you before, but that one sandwiched in between two projectors. Because that one in the subspace made by the rest, that one will satisfy the right identity, and so with that you can build the right S matrix. So the S matrix will be, S is not 1 plus V, but projector plus projected V. And then you satisfy this in the subspace. Okay, this is crucial because I stress it a lot, because there are many people I talk to, phenomenologists in particular, who are not so easy to convince about this as a mathematical crucial thing. But people who come from Batalin Wilkowiski or Faddeev Popov ghosts instead are more familiar with that. So this way I eliminate the ghosts, but I stress again that I switch from a sick theory to a new theory, because if I remain inside that, if I don't do anything radical at some point, I am still playing with the same theory. And it is impossible to achieve that goal by juggling with negative norms, states, decays, widths, unbounded or non-Hermitian Hamiltonians. But you need something like a projection. And of course, you can use this to eliminate the on-shell contributions of physical particles as well. So basically, what am I doing like this? You have the theory with ghosts. Instead of removing the ghosts, you remove every on-shell contribution of the ghosts to every diagram of your perturbative expansion. And by these new diagrams, you know where to find those. It's not like defining a new propagator and then use the new propagator in the old diagrams. You really have to do this. But it's something that you can do. So we eliminate the on-shell contributions of a certain particle or ghost, and what you do it is at every order of the perturbative expansion, actually in every diagram, in every single diagram. And then you obtain a particle that's never on-shell, which is why I call it purely virtual. So basically, if your theory contains many fields, big phi, you will say that some fields, small phi, will be physical. The others are the ones you get rid of. And then the physical subspace will be the one where you act on the vacuum only with the creation operators of the physical fields. And the complement, the B, the bad part, will be all the states where on the vacuum you act with at least one of the bad part. So as soon as you have one creation operator of the bad part, you eliminate it, and you keep only the states where you have only creation operators of the physical fields, the fields that you want to call physical. It's better if you remove all the ghosts.
Isn't similar this to do like some axial case? You're choosing some projector over some.
In gauge theories, yes.
Gauge theory.
This is not a gauge theory.
No, yeah, I'm saying in gauge theories is the same as doing as an axial gauge. Can I think of it in the same way?
No, because that is really that makes the ghosts disappear. Really,
Yeah.
here you keep them. You just remove their own shell contributions, and that's why it's a little bit more than that.
May I understand the way that you are kind of trading the bad things into gauging?
So remember that this is for theories with no symmetries.
Exactly, right? But you're changing the theory, right?
I change the
And now
theory.
you only have like virtual particles which are kind of
Yeah.
bad behaving, but I guess the effects are cancelled at the end when we compute S matrix.
Yeah, the
more
bad
like a
behaviors
gauge.
of these things are only on shell.
Yes.
So once you remove every on shell contributions, you remove the problems basically everywhere.
Exactly, but then you still have these virtual particles which are kind of ghost-like, but they're more like gauge freedoms. Is that true, or?
You do have those, and they change the physics in many things that I will tell you,
Okay.
but they're still around. But think of those as mediators.
Exactly.
They
right.
mediate interaction, like a virtual graviton, which causes the fall of objects. But these are quanta that can only be virtual
Yeah.
by their nature, because I've eliminated them, the possibilities of them to become on shell.
But it's still not a gauge theory.
This
The
is still
new
not a
theory is
gauge
still not a
theory.
gauge theory.
And indeed, I will now make the comparison between this and the gauge theories and tell you about the difference. Yes.
So, so usually real and virtual particles are related by the usual rules of particle theory. I mean, they're like inseparable.
What is inseparable?
I mean, the real and virtual particle, they're just
Yes.
they're part of the same
They are
thing.
separated here.
So what is it? What rule of quantum field theory are you breaking here in order to separate them, right? So because usually they are just described by the same field,
For example, if you use the Feynman propagator, right? Here you can separate the virtual part from the on-shell part. Well, any other prescription has a different superposition of the two. For example, if you use retarded potentials, it's a different way. In my case, you don't have this. But it's not like a different prescription. It's not like using this propagator. This would be Feynman-Wheeler.
Right.
That has a lot of other problems. Instead, it's a way to say, okay, I have to identify the on-shell contribution of something and remove it. From the propagator, it is easy, this one. From a triangle diagram, it's not that easy. But this is what does that. Instead, if you're asking what principles I'm breaking, I will tell you later, for example, microcausality. That's one, but that's not the only one.
You said locality before.
If you want, if you imagine that these objects are integrated out because you don't want them as elementary ones, it's like integrating out for the epoch of ghosts, and so you have many non-local vertices. Yes. And indeed, there is some relation in some way with gauge theories. The switch is, I want to stress one important thing, it's purely mathematical. Because there are many colleagues of mine who think that Lee and Vick, for example, Lee and Vick wanted to solve problems of ghosts by making them decay through a width. Well, you can make them decay, of course, this is good and interesting, and their idea is certainly interesting, but you do not say that the muon is removed from the universe because it decays. So it's not sufficient to have something that decays. If something does decay, it's not strictly in the asymptotic states, but once you do quantum field theory in a finite interval of time, you do have it. So it's like a projection in gauge theory. Probably there is, yeah. The projection is similar to the one we make in gauge theories. The difference is that there you have a symmetry, and here you don't have a symmetry. So that's why you have to use the new diagrammatics. So basically, in a gauge theory, you enlarge the set of fields, you enlarge the Lagrangian, the classical Lagrangian. But the complete gauge fixed classical Lagrangian is not the one you use as a classical Lagrangian for good. You have more fields, and that's good for locality of the formulation of the theory and the diagrams, with a depth of ghosts, temporal and longitudinal components of the gauge fields. And then what do? You make a projection at some point, because you do not consider the scattering amplitudes with ghosts or unphysical longitudinal fields outside. And then you know for sure that if you remove them outside, they are automatically removed from the completeness relation inside. Why? Because there is a symmetry. Here you don't have the symmetry. So my question was, can I achieve the same goal without the symmetry? And the answer is yes. And then you can ask, what if I apply this new technology to gauge theories? And you obtain the same result as usual, as always. Okay, so far I cannot embed this into a formalism like Batalin-Vilkovisky in the formalism that you use as a symmetry, because this is more diagrammatic. And but one thing that I want to stress is that every identity and every relation is algebraic. I never have to calculate one integral to implement these identities and prove them. In the case, probably there are some examples now. Never compute one single integral, apart from the integrals on the energy, which are algebraic by means of the residue theorem. And by the way, the computations with these diagrams are not so difficult, because anytime you have a cut propagator, you have a delta function. And so the whole sum of contributions, the Feynman diagram is always the most difficult one. Every correction is easier because of the delta function. There are many, however. There are many, because you don't have time ordering now. So for example, if you want to consider just a very, very simple diagram with it's a product of three propagators, non-amputative, you can have 0 cuts, 1 cut, 2 cuts, 3 cuts, and you can distribute the vertices in all different ways because there is no time ordering one. Now, with Feynman, you just have one vertex, one diagram, actually. Now you have a lot, but Mathematica can deal with those. Then I flash the bubble and the triangle just to convince you that calculations have been done, but they are all algebraic. Let me stress the box. In the paper you can find the box with diagonal, the hexagon, and so on and so forth. Okay. Another important consequence of this approach is that since you are just sending the S matrix into a function of the S matrix, you are sure that you preserve all the symmetries. Lorentz invariance, gauge invariance, general covariance, because the original S matrix is invariant. And these operations, as long as when you project to a subspace made of gauge invariant states. Okay, so let's see some consequences for phenomenology, because if entities like these exist, they can change the phenomenology beyond the standard model, for example. There is some exploration of those possibilities in these papers. Or in cosmology. Now I will skip the details here, but I will move to two specific subjects, one in phenomenology and one in cosmology. Just to remind you that so far about these new particles, there are 3 equivalent but different formulations. We don't have time to go through them. And I started from the last one, because normally the simplest one is the last one you come up with, unfortunately. So it's the most recent one. It's conceptually simpler, because it's, as I said, just using legit diagrams that you can build. And certainly they are a little bit different from the Feynman diagrams, but if you are familiar with Keldysh and the others, they are not so different. They are along the same way. Another thing is that's important is that quantum field theory is not just on-shell physics or the S-matrix. So this has been bothering me for a long time because you spend your entire life on just a subsector of a theory that's supposed to have an evolution operator for arbitrary initial times, arbitrary final times, arbitrary initial and final states, arbitrary boundary conditions if you are on an arbitrary manifold. That's what we would do in quantum mechanics. That's not what we do in quantum field theory. And so if I came up with some idea that's interesting, it must be possible to implement it everywhere. But then I had to do the quantum field theory in a finite interval of time anew because there is very little literature. Or you can find quantum field theory with a finite temperature, or you can find quantum field theory where the space manifold is a torus. Most of the times you work at finite volume, but that's just a torus, which has no boundary, and so on and so forth. So I started to study this quantum field theory of physical particles and then generalize into purely water particles in a finite interval of time and on an arbitrary compact manifold to study the same things we studied so far, diagrams, amplitude, and unitary. Very briefly, what do you find? Well, first of all, you can move all the details about the restriction to finite tau, the interval of time, and compact omega, away from the interior sectors of the diagrams onto external sources, which makes life much easier because basically the diagrams are still the same. And all the identities and the tricks I've been playing with can be reproduced. So every diagram remains the same. You have many diagrams with many different sources outside which take care of these restrictions, apart from one thing that enters the diagram, which is the discretization of the loop momenta. You will have sums instead of integrals. But for a lucky property of those diagrammatics I told you about, this is not going to jeopardize anything. You can even, if you are interested in dimensional regularization, it's interesting how you can generalize it in a very nice way to finite omega. Okay, so once you realize that finite time is a lot of work, by the way, but here I skip all of it, that you can base it on basically the same diagrams as usual, you will be able to introduce these entities, pure water particles, basically the same way with one new thing, that you have to trivialize their initial and final conditions. Because once you do what I did, you eliminate the entire on-shell contributions of the particle doesn't exist. It's not a degree of freedom. You cannot fix its initial and final conditions. So those will be zero. Normally in the S-matrix, every field goes to zero. But here we are not in infinite time. You have to say what the initial conditions and the final conditions are for any particle. And if you want these kind of particles, those should be trivial. That's the only thing. But it's still, the theory is unitary for arbitrary. The evolution operator is unitary for arbitrary initial and finite times. But there is one surprise. You will not be able to fulfill this more general property that you have normally in quantum field theory with physical particles. So, for example, if you have a kernel, you can introduce a complete state, set of states in between, and divide the evolution operator into the product of, let's say, the evolution operator on some interval, into the product of the evolution operator into a fraction of the interval, times the evolution operator into the other fraction. This is not true. And it can be seen already at the tree level. Consequently, you do not have a standard Hamiltonian evolution because you will not be able to define a Hamiltonian, for example. You have the final answer. You have the evolution operator. You don't have its origin in the standard Hamiltonian approach. You have its origin in the approach I told you. But if you do this and you multiply by U dagger, you get something that depends on both T and T dagger. So this is something that is maybe interesting to look into. When is physics may be affected by these new properties? When these particles become important. So if these particles are massive, if they have a mass, at energies bigger than the mass, or time differences smaller than 1 divided by the mass, these effects will start to become interesting physically. And what is the interest of this violation? Maybe something concerning the fact that the energy will be conserved only in an average for larger amount of times. I don't know. This has to be explored. So let me list the good things and the prices to pay. So the good things are that, I've not said it, but I say it now, in every quantization I have been performing, the Hamiltonian is bounded from below at the free field level, so all the energies of all the particles are positive, not trading the non-unitarity for negative energies, because otherwise I would not be able to claim that I'm solving something. H0 is Hermitian, same thing. The S matrix is unitary. The evolution operator is unitary for arbitrary initial and finite times. And the states have positive norms, so I've not been playing with those. But you have some unusual properties. So at energies larger than the mass of the lightest purely virtual particle, which are supposed to be massive, by the way, all of them, and in cosmology very heavy normally, you do not expect to be able to order time, events in time, past, present, and future. The same, and the same for the fact that you do not have a standard Hamiltonian derivation of this. There is another thing that I will talk about briefly in a moment, which is the interpretation of the width of a purely virtual particle, because the width is normally the reciprocal of the lifetime, and here there is no particle, so there cannot be any lifetime. Let's see, 10 minutes, yes, more than enough. Okay, so I will talk first about the widths, the dress propagators, and then about cosmology. So the first thing is, well, think of the following problem. Consider the muon. The muon is an unstable particle. How can you observe the muon or explain the observation of the muon in quantum field theory when the S matrix is defined between asymptotic states from minus infinity to asymptotic states to plus infinity? Every muon decays in the meantime. So there is something wrong, inherently wrong in this approach. You cannot describe unstable particles, and they are all gone. But we do see the muon, because we do see the muon. So I will not go through how the phenomenologists accommodate for the muon in detail. That's some cheating, by the way. That works, but as usual. But the right framework is quantum field theory in a finite interval of time. And that time should be smaller than the lifetime of the muon, by the way, if you want to observe the muon. So, for example, in this paper, I studied the propagator of a particle in a finite interval of time. Curiously enough, this is the function that describes a propagator. Normally you have a pole, right? Actually, I need to separate particle and antiparticle, so I need to separate energy minus frequency from energy plus frequency. So consider one pole at a time, and let me call that 1 over z. So instead of 1 over z, you have this function in a finite interval of time, which is an entire function. It has no pole whatsoever. So how can you describe a propagator of a particle, which normally are associated with poles, using a function that has no pole? Okay, this function has no pole. And, well, we are at finite time, so the usual paradigms do not apply. So where do you find the particle? If you plot this the real part of this, you will find that in the real part of this is very similar to a Breit-Wigner function, with a certain width that is 1 divided by the interval of time. It's very similar. It has nothing to do with that, because a Breit-Wigner function comes from a pole in the complex plane. This has no pole. Still, it's very similar to that. So this is a funny thing. And the real part is positive, in agreement with unitarity, the properties we saw previously, something like this. Not only, but when you resum the geometric series of the bubble diagrams, so if you have, so instead of having the usual delta function, you have the real part of that, which looks like a Breit-Wigner, and the width is 1 over tau. When you resum the bubble diagrams into the dress propagator, the width increases by gamma, by the usual gamma, so the total width will be something like that. And the real part of the dress propagator remains positive in agreement with unitarity. This is kind of funny, because if you want to see how the muon is observed from these arguments, you see it, and you see it emerging from the right process, which is the observation of the muon. That is some question that now you are legitimized to ask, because you are studying quantum field theory in a finite interval of time. So the muon observation emerges from the right physical process, different from what happens at tau equal infinity. And what about purely virtual particles? Well, the fact that this has no pole makes it easier to resum dress the self-energies. Okay, this makes it easier to sum the self-energy diagrams into the dress propagator. And what you find is that you can make the resummation exactly, rigorously, within the convergence domain for purely virtual particles as well as you normally do for physical particles. And phenomenologically, you find a striking difference. So now remember, I am studying a peak, like the z peak in an accelerator, but at finite time. So you see, this is the blue line. It's not clean, a clean, neat Breit-Wigner. It has some oscillating behaviors. Those are due to tau, which is now small enough, short enough. But the main peak is the usual peak, of course. So this is the physical particle. And in a regime where I can make the resummation exactly and rigorously to the end for purely virtual particles as well, with the same mass, gammas, etc., you find the twin peaks you see here. And then if you can convolute it to interpret, to introduce errors that typically you have in experimental setups. You may have, you see, this goes exactly to 0 in between. You will never see 0. You will see something closer to what is in yellow here. But simply but certainly very, very different from what you see in a physical particle. So if these things exist, they will change the phenomenology, and in some case, they will be visible already at this level. Of course, you have to be very precise. Something like LHC will not be enough precise. Different is the case of quantum gravity, and with this I conclude, because in quantum gravity you do not have the option. You can say I can study phenomenology with these particles or not. They will give different predictions, maybe to explain some new effect I will need them. Maybe not, but in quantum gravity you do need to remove ghosts, because otherwise the theories that you can build that are renormalizable are not unitary. So there you do not have the option. So let's see what kind of quantum gravity you achieve when you treat the ghost, the otherwise ghost, which is a massive spin-2 particle with a wrong sign in front of the kinetic term, in this way as a purely virtual particle. You not only get a possible, possibly consistent theory, apart from microcausality, which is, by the way, something that is confined to situations that have never been within our reach experimentally, but you find a prediction for the tensor to scalar ratio, which is here written. I'll explain where it comes from. So basically, I'm starting from this theory. This is the Starobinsky theory, which gives the Starobinsky inflation, and the Starobinsky inflation predicts this value for R, tensor to scalar ratio. You need to add the Weil squared term, which makes the theory normalizable but not unitary with a ghost. Then you need to reformulate the theory entirely in this new way, and then you need to extend everything I just said to a curved background, and then you need to be sure that this new entity, which is purely virtual to all energies in the entire spectrum from sub-horizon to super-horizon scales. And this is what leads to the other bound. So, purely virtual to all energies. So basically the prediction is as follows. The Starobinsky is right. Starobinsky inflation, the first one, in 1982 I think, is the background inflation mechanism, is unmodified here by the corrections. The spectra are modified, and the prediction is modified, but not so much. And so requiring that these entities are purely virtual at all energies brings this bound into the game, which means that I have a spin-2 purely virtual particle with a mass that's around 10 to the 13 GeV at least, because this is the mass of the scalar that in this framework is equal, by comparing to the measurements we already have, to 10 to 13 GeV. So this is very, very, very large, and the time intervals where you have the violation of microcausality, for example, are something like 10 to the minus 36 seconds. So that's why I say, even if you have some unusual behaviors, they concern intervals of time that are so short that are out of reach, and they will remain out of reach for a long time. Today, by the way, the shortest amount of time we can measure directly is 10 to the minus 80 with laser pulses. So anything can happen. You cannot be sure there is a notion of time there. But there is a notion, a T in a Lagrangian. Who knows what its physical meaning will be. But unfortunately, the window of value, let me see if I have the plot, no. The window of value, which is this window, is so tiny that once we will know the value of R, it will be impossible with the arrow to say where you are. So basically it will be a confirmation of the Starobinsky value. And who knows, some centuries we will realize there is The correction, let me show you here, is encoded in this function, which is the square root of 1 plus the ratio of the two masses, with a 16 somewhere, I don't remember where. Okay, so imagine this scalar mass is 10 to the 13 GeV. This one is unknown, could be 14, 15, 16. Unless this m chi is very, very close to this bound, there is no hope it will be possible to discriminate between the prediction I'm making here and the one of Starobinsky. Suppose that m chi is just 10 times. This is a factor 100, reverse. Sorry. So you will have a correction which will be something like the square root of 1 plus 100. So unless there is a principle for making these two masses close to each other, and there is no symmetry here. So no reason why those two numbers should be close to each other. There is a reason for having this bound, but there is no reason for anything else. I see it very unlikely to have results that are so precise so as to discriminate whether you are here or within this window. But so basically this, among the many proposals that you can find in cosmology, is the one that is preferred by coming from high energy physics, because there you have many more data, we have many more constraints, among those renormalizability and now unitarity together, and they give a unique theory and a unique answer under the assumption that there is only one scalar, the one built in the package, because if you add more scalars, you have an inflation with more scalars, then you can make any prediction you want. So this is the simplest possible framework you can make, and it has a very, very sharp prediction. And as I stress, it's very highly constrained, but not from cosmology. From modern cosmology, we have 3 measurements, basically. And we will have a 4th one or a 3rd one in a while. But from high energy physics, we have many more, and a lot of knowledge more, which is what I try to use coherently in order to achieve at least a prediction that could be, in principle, tested within our lifetime. Okay, thank you very much.
Questions? A question about divergences.
Yeah.
So, you know how to normalize the little diagram. I wonder if just start changing the over here.
Yeah, you don't have to worry here because every correction contains those cuts. For example, and when you have a cut, you are on shell. That means that you are above a threshold. So everything that's below all thresholds, nothing changes, it doesn't change. And what do you get when you are below all thresholds? The Euclidean. So once the theory is renormalizable in the Euclidean, every correction that I told you about is finite.
So the set of counterterms is
exactly the same. And that's because the counterterms concern the real parts, and here you are playing with imaginary parts for unitarity. So you are splitting the two, yes, as you pointed out. Splitting real and imaginary, virtual, and find a way to play with them separately without disturbing one when you play with the other. If you don't have it, this doesn't work always. For example, you need to have a Euclidean, well-defined Euclidean theory to start with. There should be no tachyons. You can change the sign in front of a propagator like this. You cannot change this sign. the assumptions are a little bit relaxed with respect to the usual ones, but let's say minimally relaxed, because in the end you only have to renounce microcausality and these kind of things that may occur at very, very short intervals of time.
But in quadratic quantum gravity, if you have R flow, you also have a different pole.
A different?
A different pole, like p to the fourth.
So that p to the fourth is split into two p squared. One is the graviton, one is the phi, the scalar inflaton, yes, inflaton. And then there is the third one, which is the one with the negative kinetic term. That you have to treat inside diagrams everywhere in the way I told you. So this is the crucial thing. And this will change. Yeah, another difference with respect to gauge theories. In gauge theories, you have a projection, you get rid of Faddeev-Popov ghosts, you get rid of longitudinal modes. Very nice, spectacular. That's protected by symmetry. You do not have a remnant like the violation of microcausality there. Here you do, because you are not protected by a symmetry. Because you are doing these things without that symmetry. So there are some physical consequences that are not present in gauge theories.
Is it possible to write down Lagrangian formalism for the music theory?
It will be highly non-local, because it's like saying that you insist, instead of working with Faddeev-Popov ghosts, you integrate them out, and that's a determinant. Instead of leaving A0 and A3, let's say, around, you need to integrate them out also. You can do it. People have done QED in particular, but you, in principle, could do it in gravity. That means that you have to deal with non-local diagrams. So preferably, what you do in gauge theory is you project only at the very, very, very end, and in between you use extra fields just to be local, and more or less the same is here, or just without a symmetry.
How unique is this construction? I mean, at some point you had some ambiguity, you had an omega and
Yeah.
so on. But
Yeah, that omega is not a problem. That is that parameterizes the infinite arbitrariness you have, because in that omega I can include every theory. You can even with that omega switch from phi to the fourth to the standard model, because that's the Lagrangian basically. But you are ruining most properties that normally you have, like the fact that if you have a diagram like this, you would like the projection of the diagram that's a product to be equal to the product of the projected diagrams. Once you do that, you have a unique answer. But who knows, maybe nature will not need these. These are formal requirements that lead to a unique answer, but ultimately it's only a lack of data that make us struggle like this. Otherwise it would be much easier to know what to do and what to discard, of course. So let's say that it is unique within the set of the approach that's most conservative as possible, so touching as little as possible with respect to what you do normally. But certainly now you have some freedom that you could that could even be relevant physically, because I'm not one of those people who believe in beauty, symmetry, those things. I think nature defines what it is. So I do not choose simplicity over complexity.
But should I still think about this as an effective theory, like at some point?
No, this is a fundamental theory, precisely because you remove the thing, you eradicate it mathematically. Otherwise, yes, if you play like Lee and Vick and the others, you have a theory that is good in certain regimes, but every time you have a ghost, if it has a mass, there is a regime where it is negligible. So that is And by the way, this is also the reason why I can make this prediction in cosmology. Because there are something that's not familiar to most high-energy physicists, by me at the beginning, is that in cosmology, differently from high-energy physics, when something is heavy, you cannot neglect it. So in high-energy physics, when you have a very heavy particle, you say, oh, I have low energy, it doesn't matter. And in cosmology, the spectra that you study are at low energy, so-called, super horizon limit is called. But there, instead, you cannot make predictions at low energies, just sitting at low energies. You have to first well assess the whole energy range. For example, you know about the Bunch-Davies vacuum condition. Very much disputed because it's a condition on the ultraviolet limit, the sub-horizon scales, which are out of reach by definition. We'll never be able to make an experiment there or observation. Yet we impose those conditions. Otherwise, you do not get the usual predictions. And so they are rightly disputed. But they are also very well used because they are so simple, very much used because they are very, very simple and natural. So first I have to be sure that my things are purely virtual in the entire energy spectrum, which gives the extra bound for the prediction. And then I can make the prediction. But this is something I can do because precisely I have this new notion. People who have ghosts, for example, in the ultraviolet sub-horizon scales, they have ghosts, free ghosts with a frequency that's time independent. What do? They mimic the Bunch-Davies condition, but it's something not very, very justifiable, I think. And they do not find this prediction. Indeed, in their case, they find the Starobinsky. Everything below the Starobinsky limit is good for them. Not this tiny window, but everything, every possible value, because they lack the other things. So yes, it's as fundamental as it can be, because you know every fundamental theory in the history has become effective after some time. So, but you can view it as a fundamental theory, like the standard model, which may not be, but.
Except give up causality at a very high scale, or very short scale.
Okay, this I understand what your concern is, but the question is why should there be causality? So you can advocate causality or not, because this is not the physical principle, and in quantum field theory, by the way, just the standard model, the notion of causality is already there, very, very weak. I don't know if you are familiar with Toft and Veltman's diagrammer. They put a warning there because there is no consensus of what causality is, what it means. In gauge theory still. So I think that causality has been renounced long ago, long before these things. But here, it's really gone, below a certain scale. Here it's gone for sure. So that I would not consider a minus.
It's a fundamental step.
I will continue with this finite time formulation. So if I remember correctly, the standard argument there is that you need to look at infinite time for estimating, only because otherwise we cannot easily define in and out states.
Yes.
Because we define it in field theory.
Exactly.
So what happens to that problem here?
So here you are computing the transition amplitude, as in quantum mechanics, between an arbitrary state, an arbitrary initial configuration, which is not defined by particles, and an arbitrary one. Let me, however, tell you that as soon as you will plunge into this problem, you will discover that you need to use coherent states with which you can do everything, but they are as close as possible to the notions of particles. Without that, you will have a lot of complications.
More questions?
If not, let's take them again.